On July 22, 2009, neuroscientist Henry Markram walked on stage at a tech conference in Oxford, England, and told the audience that he was going to simulate the human brain in a computer, so that this computer will have his own idea, will be able to make his own original ideas. In 2013, the European Commission awarded his initiative, the Human Brain Project, a staggering €1 billion grant, worth about $1.42 billion at the time. His timeline was ambitious. "We can do it with 10 years, said Markram.
And if we do succeed, we will send to TED in 10 years a hologram to talk to you.
After 10 years of effort and a diarrhea of money, the project failed. The supercomputer that consumes 20 megawatts, that is 20 million watts of energy, failed to simulate the brain that consumes only 20 watts of energy. We all know the story. Archimedes is sitting in his bathtub when suddenly a brilliant idea came to him out of nowhere. So he walks out to run in the street calling Eureka, meaning I found it. Newton, watching an apple falls off of a tree. Well, Eureka. Einstein in Baden office with his happiest thoughts, a fat man falling off the roof. Well, Eureka. It's always the same story. A great idea coming out of nowhere to a genius when he's doing nothing. It weirdly comes at the time of rest, when your mind is silent, thinking about nothing of significance, at the time when your brain consumes the least amount of energy. It is just mysterious that your brain is capable of producing such a big ideas while consuming such a small amount of energy. And the question now is, where does those ideas come from? Well, first, what are ideas? I mean, we all know what are ideas, right? They are those images in our minds. They are the thoughts, insights, memories, and the inner voice in your mind. But just like the images in your phone don't be stored as an actual paper-printed images, rather a zeros and ones represented by electrons in the transistors in your phone processor. Your ideas also being stored and processed in your mind as what we know as the neural synapse. A synapse is a junction between two neurons. The neurons in your brain are naturally unexcited, having barely any energy within themselves. A state we know as RMP, the resting membrane potential. It's called RMP, and RMP stands for resting membrane potential. When you see something, when the photons of that thing hit your retina, your eyes neurons deliver this electrical message with a frequency proportional to the wave frequency of the photons to your visual cortex, right in the back of your head, which itself consisted of a huge jammed chunk of neurons. Those neurons themselves, when receiving the message, undergo a high energy state, a state we know as AP, or action potential. So how to get rid of this surplus of energy? Well, they actually send it to other neurons throughout the junctions, the synapses, and those other neurons send it themselves to other neurons, and so on. And this energy firing of this huge network of neurons is what we believe to make you reconstruct the images you just saw, while another network of neurons is responsible for making you understand and comprehend these images you just saw. Now, we don't know how the whole process works, and we still don't know so many details, such as how this simple firing of networks of neurons gives birth to the stunning complexity of your conscious experience. But we know that each network of neurons is associated with a particular function, like seeing, hearing, smelling, sensing, and imagining things. Now, during the process of passing energy throughout the network as an electrochemical signals, the connections between the neurons, the synapses, are getting stronger and stronger each time. So it's becoming easier and easier to use this network the next time. In other words, every time you see, hear, smell, sense, or imagine something, it becomes easier for you to remember it and to think of it in the next time. And this is how the process of learning happens. Use different networks at the same time, and you start to merge different images and sounds, etc. You just start to form mental models of reality. You just started to form insights, and by insights, perchance, opinions. You just started to make ideas. So ideas actually have an actual tangible material basis. It's the neural networks and their synapses. Ideas are the experiences we get when particular networks of neurons fire together in our minds. But there is another kind of ideas we don't get from outside. We don't learn. Ideas we generate ourselves by the process of creativity. For a moment, it seems magical, like it comes from the absolute nothingness. A sudden idea pops out in your mind. Something, sometimes without even seeking it. It's the aha moment, the eureka. Where does this original idea comes from? To answer this question, we have to study the brain activity during the magical appearance. I mean, nothing magical, but you get the idea. During the magical appearance of the original idea, during the practice of creativity. A recent study performed a fMRI brain scans, a functional magnetic resonance imaging brain scans, on 163 participants while doing a divergent thinking task. That is, a task that requires participants to explore creative solutions to, commonplace or common problems. The participants were given a commonplace object and were given 12 seconds to come up with a creative application for this object. Creativity was here defined as new and useful application for these commonplace objects. For instance, if the object was a paperclip, an uninspired answer would be, attaching papers together with this paperclip. While a creative answer may be like using the paperclip as a needle. Analysis of the brain activity from those 163 participants revealed that highly creative thought was correlated with increased activity within 3 different networks in the brain previously found critical for this type of thinking. Number 1, the executive attention network, or known as central executive network. Number 2, the imagination network, also known as the default mood network. And number 3, the silence network. The executive attention network is responsible for targeted attention and focus. As we all know, however, the human attention span can be incredibly short, and the executive attention network often switches rapidly with another networks, especially the imagination network. Now, the imagination network is integral in creative activities such as brainstorming. It is also responsible for social cognition, such as our ability to understand what someone else may be feeling or how to react in a particular social situation. Now, this network is sometimes viewed as the genesis of creative thought, as it is the network in control of performing mental simulations. However, it is the interacting of the spontaneity of the imagination network and the focus and sharpening tools, let's call it, of the executive attention network that yield the true creative thought as a final product. And finally, the silence network is in charge of monitoring the internal stream of consciousness, as well as external stimuli and events. This network makes the decision as to which information, internal or external, is most adept at solving the problem at hand. And it is really, really important in switching between various brain networks. For example, the silence network is in charge of taking the massive amount of sensory information that you are being bombarded with constantly, and choosing which sensations, which information we should pay attention to, and which we should not. Simply put, the imagination network is like a popcorn pot of previously learned ideas. It takes hundreds of thousands of ideas and subconsciously deassemble them and reassemble them into new different forms, and all of that happens, again, subconsciously. But of course, you cannot spontaneously, consciously comprehend and validate all of the new thousands of ideas. Here comes the validation guy, the silent network. It subconsciously, superficially, and transiently checks the practicality and the usefulness of those new ideas and choose only the useful ideas. And non-silently, the silent network send those few ideas to your executive attention network. This right moment is the aha moment, the eureka. It is where you finally be aware of those few ideas and start to consciously, deliberately, and carefully examine those ideas. So original ideas do not pop out of nowhere. They are just new forms of previously learned ideas, maybe even a formulated composition of them. And this explains why you need to be knowledgeable about a particular field in order to come up with a new big thing in that field. Not just because you need knowledge to examine the practicality of your original ideas in this field, but because you actually need this knowledge, this sea of ideas, in order to make your brain have enough, let's call it raw material, to build new original ideas. Yet this does not explain the energy efficiency of the brain. How could it be possible that a supercomputer that consumes 20 million watts of energy failed to simulate a human brain that consumes only 20 watts of energy? It's insane. Here's a question to you. Can you recognize the following faces? Well, here's another question. Can you tell the answer to this question? Take your time. Well, don't worry. I mean, most people face difficulty answering such a questions. The real question we're trying to answer in here is why? Why is it so easy for you to recognize a celebrity face and so hard to solve a math problem, while it is hard for a computer software to recognize the faces and so easy to solve the math problem? This is the subject of this book. The bestseller and one of the greatest books I've ever read in my life, Daniel Kahneman, Thinking Fast and Slow. Now, in his book, Kahneman explains how your brain works in two moods, System 1 and System 2. Now, every time you drive your car, you take a shower, drink your coffee, or, recognizing a celebrity's face, you're using System 1. It is not really effortful, doesn't require lots of energy, and during the usage of System 1, the energy is widespread across all regions, nearly all regions of your brain. Well, every time you solve a mathematical problem, plan your trip, or study, your brain works in System 2. It utilizes large amount of energy to specific small regions of the brain to perform a small number of tasks, and they require quite an effort. Now, intuitively, you would think that most of great original ideas emerge during the usage of System 2, the slow, effortful system during the process of a deliberate examination of an issue. The reality is, no. Almost all original ideas emerged in the minds of great people during their usage of System 1 in a relaxing, lazy situations. So why? This question made a lot of people think of a hidden factor that we don't consider when studying the brain. One of those people is this man, Tim Palmer, a mathematical physicist who spent most of his life dealing with the complicated systems of weather and climate, and how to predict them. If there is something he learned from his career, it would be the importance of stochasticity. Is that even a word? Well, it's just randomness. During his career, Palmer noticed that adding a stochastic factor into the process of predicting the outcome of a complex system governing the weather, for instance, would indeed increase the efficiency of the process by decreasing the amount of energy needed. Indeed, Alan Turing himself, the father of modern computers, once talked about adding a stochastic factor to his Turing machine, to the computer, in order to enable them to solve long-tail problems, which are problems that require a long time and lots of energy to be solved. According to Palmer, this exactly is the case in the brain functionality. Palmer argues that during the usage of System 2, the high energy passes throughout the neurons allows majorly the mainstream pathways of the neural networks to be activated. That is, only the learned ideas are being used. While during the usage of System 1, the low energy passes throughout the neurons allows majorly, all the pathways of the neural networks to be activated, including the small peripheral neurons. It is here, Palmer says, an important process might take place. A seemingly stochastic opening and closing of the gates of the synapses, perchance a stochastic firing of the peripheral pathways, which itself leads to maybe a forming of new pathways in a sudden stochastic way. In other words, new ideas. But wait a minute, did I just say stochastic? I mean, where would stochasticity come from in a classical physical system like the human brain? Ah, come on, not again. Nah, I'm not doing this. Quantum mechanics. According to Palmer, creativity might be a side result of an evolutionary process to develop the most energy-efficient systems, which by some mutations allowed for some quantum events to take place in a small neurons with axon diameters less than 0.3 millimeters, which might have had another side result. Now hold on a second. We actually cannot talk about quantum mechanics without talking about this. So if you love physics, you probably know this experiment, and it's actually the foundation of the quantum mechanics. And the experiment is actually fairly easy. We just need a quantum particle, that is, say, photon or electron. And here, just let's assume that we have an electron. And, well, a screen, a black screen, right, just a wall, you know? And in here we have a screen, another one. Now, according to Copenhagen interpretation, which is one of many interpretations of quantum mechanics, the particle, the subatomic particle, the quantum particle, and here the electron, behave as a wave if we do not observe it, and as a particle if we do observe it. So, assuming that we're not observing the particle, which way, if we show this particle, which way it's going to go? Will it go throughout the first split or the second split? Well, now, according to the interpretation, it will just go to both of the splits as a wave, and so we're going to have two waves. And what's going to happen is that those two waves going to interfere and going to have this, or going to make this pattern on the screen of black and white, or light and dark periods, let's call it, on the screen. And This is resolved from the addition of two waves, okay, and it happens all the time. You can do it actually with even a water waves. And so if we want to predict what gonna be the pattern here on the screen, we only need to add the two waves. We add the amplitudes of the two waves to each other. Now there is this story, or it's probably a legend, of a professor in some university who was explaining to his students the double split experiment. Sorry. And so one of the students just raised his hand and asked the professor, what would happen if we didn't have two slits? What would happen if we had actually three slits, as you can see? So the professor went on and answered the question. You just add the amplitudes of the three resulting waves, and you get the new pattern. So the student asked again, how about four slits, as you can see? Well, I mean, the professor just said, you just add them. You just add the amplitudes of all the resulting waves. But here, the student actually went on to ask, how about an infinite number of slits that we don't have the screen anymore? What would happen? So, according to the story, this student was the famous Richard Feynman, and his question will be the foundation, the basis of the amazing theory of the sum over history, or so-called the path integral formulation, that postulates, according to this theory, that a subatomic particle, when trying to transfer from point A to point P in here, will actually go through all of the paths possible to get to this point in space-time, and we just go on to, well, hundreds of thousands, millions, in fact, infinite number of trajectories. Now, the theory is, of course, much more complicated than this, but the point I want to get in here is that the subatomic particle in here go throughout all of the trajectories possible. Most of the trajectories cancel out each other, but it still go through all of them. That's a banger. Pollard builds upon this concept to hypothesize that during the transition of the neurosignals, the chemical electrical signals from one neuron to the other throughout the synapse, all the possible trajectories of these transitions actually happening, which results in two things. Number one, each neuron is actually capable of computing thousands and thousands of possible scenarios, each one neuron. And number two, if in certain conditions a neuron outputted a certain result, a certain output, this same neuron, let's call it Steve, this same Steve can result a different output in the exact same conditions, which means if we define free will as the ability to make different decisions when put in the same exact conditions, this means that you do have free will. And if this is not enough, it also explains why do we need thousands or even hundreds of thousands of scenarios and images, whatever, to train a machine learning software, while we only need a few handful of scenarios to train a human to perform the same task that the machine learning software is trying to perform. But hold on a second. Did I say that those trajectories just pop out of nowhere, of the absolute nothingness, and they're always there, and so hundreds of thousands of them? Well, I mean, if every one of them leads to the formulation or leads to the making of new original idea, or at least if every one of them is capable of making new idea for some extent, does that mean that new original ideas do come out of nowhere, from the absolute nothingness? For me, if you ask me about my opinion, I honestly don't know if this theory could be adopted, if it's true or false. But I think that so much research is needed to validate this new theory. And until some genius, find out if we can adopt or debunk this theory, the only thing we can do is to keep thinking. Always keep thinking.